Hi, everyone. Thanks for joining us. My name is Jennifer Rogers. I am the outreach coordinator for LibreTexts. I am going to let Krystal introduce herself, and she is going to tell us all about using LibreText for her chemistry courses.
Hi, my name is Krystal Grieger. I'm a graduate student up at North Dakota State University, and today I want to tell you guys about how we use LibreText to create student-generated OERs within our organic chemistry labs. And so, in terms of organic chemistry, green chemistry, there's been a major push to integrate it, but it hasn't been integrated into the textbooks very widely. So green chemistry and sustainable chemistry includes things like the 12 green chemistry principles, which have been around for a while. It also includes things such as the planetary boundaries and the UN Sustainable Development Goals, and trying to implement those into the textbooks. And so since they're not widely introduced, we thought that we'd have our students help create pages that can go along with the Organic Chemistry 2 textbook that relates the reaction students learn in Organic Chemistry 2 with the material that's actually relevant to green and sustainable chemistry so that they can be taught side by side. And so what student-generated instructional materials are artifacts that students create that you use in learning process. So an OER would be an example of this. And so students often exhibit greater learning gains when they are using student-generated instructional materials because they're written by near peers versus by experts who use a lot more lingo that they're not familiar with. And it also correlates well with the Next Generation Science Standards, the SEP, obtaining, evaluating, and communicating information, as well as high impact practices as being part of collaborative assignments and projects need portfolios. And so when we were looking at where to use and where to create this OER for our students, we wanted it to be something that was widely utilized and that we found LibreText fits really well with. It's used in a lot of campuses. And there's also really great support with this if you guys are interested in doing it. Dr. Demar Larson has office hours twice a week, and he is super helpful in them. So you can get guidance on how to have your students get through this project and how to develop it. And it was also really easy to use, both from the faculty side as well as from the student side. And so what we did for ours is we had a majors organic chemistry 2 laboratory with 19 students. And since it's majors, they meet twice a week for 3 hours. But due to the pandemic last year, we had our students complete in-person experiments on alternating weeks. So every other week was virtual. And so during the remote weeks, we worked on completing this project and doing virtual lobster experiments. And so this activity was 16% of their final grade. Other things that they had were lab reports and quizzes and the exam, and then problem sets and worksheets. And then we also wanted to see what impact this had on students' cognitive learning gains as well as what their perceptions were. And so we analyzed the impact of the project using a pre and post design. And so our project goal was for the students to create an OER page for a selected reaction from Organic Chemistry 2, which the page should encompass the following. So we had them break it up into 5 different parts. We wanted them to find information about the reaction. We wanted them to write out the reaction mechanism. We wanted them to see the use of it with a bioderived molecule, to look at that example that they found and its adherence to the green chem principles, and to connect that research to a planetary boundary. And so we'll go through those in more detail in just a minute, but I'll show you guys what we used for their overall project first. And so the learning objectives, we wanted 5 different learning objectives. We wanted our students to see real life examples of the reactions and then to be able to evaluate it using green chemistry principles and planetary boundaries. And we wanted that because I know from when we were in undergrad, a lot of it is more memorization, and we wanted students to see that there are real life examples. It's not just a reaction in a book that you memorize and move on, that there's actual applications, especially since these were chem majors. And then we wanted them to calculate the process mass intensity and the atom economy of the reactions in order to help evaluate their greenness. Process mass intensity is one equation that's used widely in the chemistry world for evaluating it in industry. It's one of the gold standards, as well as atom economies, also used frequently. And then we wanted students to make connections between the concepts in organic chemistry, green chemistry, and real life practices through the creating of their art, as well as reviewing their peers' OER, so they could get experience with not only their own reaction that they're learning about, but the other reactions as these students are in our Chem 2, so that they get more knowledge to be more familiar with it for their course. And then we wanted them to develop information literacy by being able to locate, evaluate, and use literature articles, especially to be able to use SciFinder and Google Scholar, and to be able to evaluate if they find a primary source, difference between primary, secondary sources, things like that. And then we wanted them to develop professional communication skills by being able to create an OER that would be designed for other organic chemistry students, and also by discussing scientific discourse with their peers. And so we broke this project up into 6 phases, which encompassed each of those 5 pages that we showed you just 2 slides ago. And so we wanted to start it off pretty easy. So for the first phase, we just had them pick a reaction and then draw the reaction mechanism. Then we had them write the intro for the reaction that they chose. Want them to find their literature article and summarize it for phase 3, and then make a connection to the planetary boundary. In phase 4, after we had time to confirm that they all found appropriate literature articles, we had them analyze the greenness. And then we had them create their web pages on LibreTexts on phase 5. They got peer review on that, and then they moved on and submitted the final draft. And so when we use for peer review, one of the programs that we found really useful is this Feedback Fruits peer review software. It allows you to upload web pages, PDFs, Word docs, many different files. And the students have to respond to each part of the rubric that you put in there. So they have to evaluate it, indicate how much it was matched or not matched, as well as like give a comment to the person that they're reviewing it for. And so I just kind of gave you an example of the description that we gave for when we had the students evaluate each other's reaction mechanisms for the first step. And so by creating the rubric, and that was one of the best parts about this software, is it let you create your own rubric. A lot of the softwares, when we were looking at them, they gave you pre-made somewhat rubrics where you couldn't fully tailor it, and the software does. And they've still been doing where for each university you can get 5 free copies. And so overall, as I said, for phase 1, we gave the students a list of 39 key reactions that we picked out from the textbook, and let them pick between that list which reaction they were going to pursue for the semester at the beginning of the semester. And then we had students use free chemical drawing software to draw the reaction mechanism for that first step after they picked their reaction. And so we let them use things like Biovia Draw, Marvin Sketch, or ChemDraw Direct, so that way students wouldn't have to pay for it. One thing I did discover when I was on phase 1 is when the students turned in their work for their mechanisms, they kept turning them in incorrectly, which caught me off guard. And because I know kids, when they turn things in, they want to do it right. So I was wondering, so I just asked them, like, hey, what's going on? Why are they turning them in funny? And then my kids explained to me that they were intentionally changing the answers just so that it wouldn't be plagiarized, since most of these, being as they were well-known reactions, they have well-known mechanisms, and they didn't want to turn in the mechanism that's already been reported. So they were intentionally like trying to like change it to something else that wasn't quite right, just so they weren't plagiarizing. So then that allows for like the discussion with your students of, so if you cite it properly, you say obtained from, and you actually cite it as that this is a known one, this is where you got it from, that's okay. So if you guys do recreate this project, I would recommend ahead of time, instead of like after your kids turn in their assignments, letting them know that if they turn in a mechanism that's a known mechanism, it's okay that it's the same as what's already known. For the second phase, we had students draw the general reaction scheme after they turn in the mechanism, just so that we had like an overall one that we could put at the top of their webpage. And then we had students identify, because by this point in time, they had been well-versed in course on the different types of functional groups. And so we had them identify what functional group that reaction started with and what that functional group became after the reaction. And then we had them go through, because at that point in time, they're also looking at protecting groups and had covered that. And so we had them identify what sensitive functional groups would be in that reaction. And so that would need protecting groups. And then we had them write the description for the reaction mechanism after they had turned in their image of it, so that we could check, make sure the image was right before they worked on typing out their description. In this phase, the one thing that I did note, you do have to be very clear with the students, the difference between a mechanism and just the general reaction scheme, because a lot of kids weren't familiar with what the difference was. So I know that's one thing that next time I'm going to make sure that at the beginning I explain, okay, this is a mechanism, this is a scheme, and this is why they're different, because in their minds, it's the same thing. No, but by the time you explain it, then it's not. But that was one incorrect conception that was at the beginning of that. For the third phase, we had them look up the earliest report of the reaction and then look up some modifications that have been made since, whether people changed solvents, found ways to lower the temperature, or just different things to make the reaction better in some form or fashion. And then originally I was going to have them read the earliest report until I found out before, when we were getting in the planning phase of implementing this project, before we implemented it, that the students' reactions, some of these earliest reports are either hard to find or they're not written in English. And so we had them just locate who wrote it so that they could say this was first reported by, or the earliest report we found was by, instead of actually having them delve too far into that. And then for the second one, we wanted them to find a primary literature source in which the reaction was either bio-based or used a bio-derived molecule for the reactant product or catalyst, because we wanted them, since that's one of the green chemistry principles for use of renewable feedstocks, we wanted them to actually see if they could find a reaction with this. And so here's where we taught students how to use SciFinder, because I wanted the students to be able to actually research and use SciFinder and learn how to use SciFinder. SciFinder, I found out, is harder for students to use right away, so you do need time to practice with them, and then have them submit the paper that they pick ahead of time, just so that what they pick actually does, if you are going this way, use that bio-based molecule, because a lot of kids weren't sure how to tell if a molecule is bio-based. You have to show is how do you actually backtrack if this is a bio-derived one or not, if it doesn't specifically say in the title or abstract. And then we had them draw the reaction from the article that they chose, and then summarize just key findings of the study. And then to those planetary boundaries that we showed you on the first slide, we wanted them to connect whatever that research was to one of those planetary boundaries, and if it would help that boundary or if it hurt the boundary, what impact that reaction would have on one of the boundaries. And then for the next phase, phase 4, we had students analyze the reaction for its adherence to the green chemistry principles. The students found this one pretty easy to do, because we had been discussing the green chem principles for this semester and the previous semester. And then we had students calculate the green chem metrics for atom economy and process mass intensity. And then for process mass intensity, since a lot of papers don't write out the quantities used for all reagents, if there were reagents that were missing for like in the procedure for quantities, we just had students indicate that we couldn't calculate the full process mass intensity, these quantities were excluded. And so then we get to phase 5, where the students were actually starting to work with LibreText, because after each of these phases and during each of these previous phases, we had them go through peer review using feedback fruits. I gave them feedback and then they could do revisions. And then once they were at that point, then we started having them upload the information into LibreText. Students sent me I had students send me their figures for converting them into SVG files. Because the free softwares do not give SVG files. I later found out that it's okay if you can't get the SVG files. I would not recommend doing that as a time, again, unless you have a very small class, because it does take time to take those files and convert them, because a lot of times when you upload them into ChemDraw itself, the files get corrupted a bit, so the arrows aren't quite where they are, so you kind of got to drag stuff back around. And so, but I made the SVG files, sent them back to the students. And then we discussed using alt text for images in class, which was a new concept for many of the students. And I know at least a couple of them said it was kind of cool because we addressed how you can use it on social media like Twitter, Facebook, etc. And so some of the kids says that they were actually going to start implementing it there because they didn't know that was a thing or how to do it. And so that was one of the perks of doing it this way, where they actually had to learn about what alt text is and how to do it on here. And then when we're talking about in class, we also watch like videos on how to do it on Twitter and why it's important. And so that was useful for the students. We used that MathPicks snipping tool to convert the equations into LaTeX. That part I know the students had a bit more problems with, but if the ones that had problems were the ones that, because this was during the remote weeks where they had to sign into Zoom, and they were kids that missed that time period. Those students that were there and did it in class as a group like the rest of us did were okay. But some students, as you guys will see later, said that was a harder part. And then after they finished getting everything uploaded, we had them turn it in and they gave each other their final peer feedback, which led to submitting the final projects and then having students sign permission forms if they want their pages to be available online. And so overall, we wanted to assess, as I said, we used pre-post designs. We wanted to see what kind of learning gains were. And one of the things we did was we had students give a self-assessment of their learning gains. And as you can see, for the most part, students agreed that they had a better understanding of how green and organic chemistry connect because they had to actually research those connections. They indicated that they had a better understanding of how both green chemistry and organic chemistry relate to real life applications. I was excited to see that a lot of them indicated, almost 84% indicated that their interest in organic chemistry increased as a result of this project. As well as they indicated that their knowledge about organic chemistry increased by actually delving into these reactions and seeing how they apply to real life and not just as here's the mechanism from the textbook to memorize. And so we also wanted them to report their self-assessment of their skills that they gained. And so they indicated that they were more comfortable explaining it to a general audience. Being able to use a chemical drawing software was about a 50-50 split, which was kind of surprising, but then we also had to use chemical drawing software in the fall semester for those software. So I think that and we had much better response for positive on that statement when we did it in the fall with their infographics projects. So I think that was partially due to the fact that the students had already been exposed to the software previously. And then we had them look at if they were more comfortable using SciFinder, which most of them agreed that they were. And so that was advantageous because at the beginning, using SciFinder was a new skill for them. And then we had them talk about if they understood the difference between primary and secondary sources, because both this semester and in the fall semester when we had them, and they were looking for literature, a lot of them would turn in lit reviews or textbook chapters or things that aren't primary sources. And so in both semesters, we had discussions on, okay, this is primary, this is secondary. And so, and in both cases, when we tested their knowledge about it later on, is they were much more capable for addressing the difference between them and when to use each. And so we also wanted to see not just their interests and self-reported, but we wanted to actually measure it because there are cases where self-reported measures can be overestimated. And so before and after we implemented this project, we had asked the students a prompt that we obtained from the JChemEd article from 2019, which asked them to take 2 generic reactions and think about what factors they would consider to decide which one is greener. And so they needed to use complete sentences and explain why they'd be considering that and like what impact it was. And as you can see, there were a lot more principles addressed overall in the post-test than there were in the pre-test. And as you can see, item 10 has no response in either because in the prompt they were told to assume that you're making the same product. And so it won't be a factor. And so This one isn't quite as stark of a contrast, partially for the reason, well, you can see that there are more in the post-test addressed. One limitation of this is that the students had already been taught about this in the fall, and so the stark change between pre and post test is more muted in the fact they had already been previously instructed on the green chemistry principles. And so we gave students an instrument that we developed that we call the AskGCP. It's assessment of student knowledge of green chemistry principles. And so we calculated their normalized learning gains. And so what a normalized learning gain is it allows you to measure how much the student scores increased. And so you take the score on the post-test minus that of the pre-test and divide it by 100 minus pre. And so these are our learning gains over here on the left-hand side. And then across our x-axis, we have the score that they received on their pre-test. And so, as you can see, as you get closer to the higher scores, they don't have a gain because they were pretty close to already having a perfect score. But overall, a 22% learning gain was observed. And so we can see that they were able to score higher on assessment afterwards. And we also calculated the Cohen's D, which is the standardized mean difference between the pre and the post test. And Cohen's D was 0.708, which indicated that on average, student scores increased by more than 2/3 of a standard deviation. And so we wanted to see the student perceptions of the project. And so in an open free response box, we asked students what aspects of this project were beneficial. And then in another free response box in the survey at the end of the semester, we asked them what aspects they would like to change. And the things they thought were beneficial about this project is they really liked the peer review and be able to give and get feedback. They also like to be able to gain a deeper understanding of the reaction mechanisms, as 3 of the students wrote that as one of their responses. And learning about various reactions kind of ties into that as well. It was actually surprised that 2 of the students, for when they were asked what was beneficial, they wrote out that they were able to distinguish between primary and secondary sources, so they themselves felt that was like helpful for them. And they also appreciated having enhanced familiarity with the chemical drawing software, and that they liked that the assignment was formatted in phases. However, on aspects of change, they also indicated that they would have preferred that the phases were in the same order as the book pages, instead of where we try to break it in easy, where draw the mechanism, since these are known reactions, they're in your textbook, they're online. And so we try to break them in that way. They would have actually just preferred if they had, or at least 3 of them would have preferred if they were in the same order right away as what the book pages would be. The less comments for the last phase of feedback fruits, that one could almost be ignored because that was just my bad. When I uploaded them, I had them submit all 5 pages to their LibreText on one site, thinking that it would break them up into 5 different pages. I found out that feedback fruits, if you upload 5 pages, all 5 pages go to one person and 5 different pieces. And so the rubric ended up having all of the stuff for all 5 pages go, and then you'd have to do it for each page, but it wouldn't let you skip the sections that weren't for that page. So for that one, it would just be make sure you make 5 separate feedback fruit assignments for submitting. So that one was just on me. And then 2 people said they would have preferred if it was done in person. And then when I kind of probed the class later on, they had said is that it was kind of harder doing it remotely for getting help versus if I would have been in the room with them and able to like see their computers instead of just through Zoom and breakout rooms. And then 2 also indicated they wanted to see the project started earlier in the semester. We had put it off just a little bit because we wanted to wait until the students were at the point to start seeing reactions before we got there. And so we also asked students about their perceptions about LibreText itself. As you can see, most says that adding text to the pages to LibreText was very easy. And it is, it's just typing it pretty much just like it's a Word doc. I was a little bit shocked that I got such a broad range on uploading images, because that's just drag and drop. But I also know that by that point in time in the semester, some of the students were missing, and this is a small sample size, so I don't think it would be as broad of a range had everyone been there when we were doing it together in class. But that one, some of the students struggled with or indicated that it wasn't as easy as other things. Formatting your pages, again, was kind of a broader range, but that was things like putting in your header, adding alt text, and things like that. And again, that one kind of also just depended on if the students were there or not. And then the one I wasn't too shocked on that they had a bit of difficulty was using that MathPicks snapping tool, which is a really cool tool. You can like just drag and highlight over what the equation is that you want converted into LaTeX, and it spits out how to put it in LaTeX, which is super awesome. But some of the students did struggle with that one a bit. And I know even when we were in class, a few of them were, because once you get it copied, then you have to make sure you get it copied right when you put it in. But overall, as you can see, is all the way down, some of the students felt it was very easy and others agreed that it was easy. And so we also asked students if they would want to see this incorporated into future lab courses or future lecture courses. And it was almost an even split both ways. So 60% said that yes, they'd want to see it in future labs, and 67% said yes, we would like to see this incorporated into future lectures. And then in both cases, 33% said no. And for labs, 7%, which was one of the respondents, says is that they're not sure if they'd want it to be incorporated into future labs or not. But overall, as you can see, if you're thinking about having your students start creating OERs and help build this wealth of resources that are out there, at least from our students, most agreed that yes, they would like to have this incorporated and done in future classes. And so here's just some examples of work that the students turned in. As you can see for this one, for one of the intro pages, they had their general reaction scheme. They gave the summary of the development, they gave the utility of the reaction, and they included their citations. And here is one of an example which they reported for one of their reactions for their selected one from a study. And they give the reaction scheme for that they drew out. And they give what the purpose was and what the findings were for that study, and then the reference for their chosen study that used that reaction from the textbook. And so looking back at incorporating it, some of the lessons I learned is that, as I said, is that you should definitely address ahead of time that drawing a known mechanism with proper citations is not plagiarism, because the kids were trying. And so there was like some frustration because they'd be like, no, here's the pages, look at the mechanism, and then they send it back and it would still be different. And it was just that they didn't want to risk being plagiarizing it. So that's why they were intentionally messing it up. And some students will struggle with finding scientific literature. So it would be helpful to have time set out, especially now that we're back in person, that you have them, and that's where kind of what they had indicated in the survey too, is that if while they're looking for literature, if you were in the room with them while they're using SciFinder and learning how to use it and how to find it and how to decide about the reaction that they're looking up. And then to actually take time in class and show them that when you're drawing a mechanism, you can indicate that you don't care about anything else but this functional group, what the reactants are that's used in that reaction, what that desired product is in that search, and that'll help you narrow down your search easier than just like some of the kids were before, like we sat down and practiced it. When they were trying to work ahead, they just went into Google Scholar and like typed in the name of their reaction, which for some of the well-known reactions that worked, but for a lot of them, for the like not named reactions, you aren't going to pull up as many options when you just go through Google Scholar versus actually taking it into SciFinder. Regularly check with the students where they are at in the project, whether you do it through a Blackboard discussion board, check with them in person, just make sure that you know where they're at, because some of the kids will be right on task and other ones will be lagging. And especially when you want students to give each other feedback, you kind of got to keep everyone kind of pulled together by the time they submit it, so that everybody gets feedback and everybody has time to. because I know that's one of the things is we kind of kept giving extensions, which is why I think a couple of kids want to start it earlier, is we still would have been done way in advance. Just we gave extensions to get everybody caught up, and then it ended up pushing right to the very end of the semester. And the students will need guidance when they are inserting their questions using LaTeX, as well as final touches such as adding alt text and formatting headers. That'd be great to do, kind of like what we did for the ones that were able to make it that week, as we did it in class with breakout rooms. And so some general conclusions is that student-generated instruction materials are instrumental. They do engage students. Our students were working remotely with everything going on, and they were highly engaged with this project. They promote learning, because you have to think about it not just as here's something I need to memorize, but now I need to think about enough so I can explain it to someone else. And it prevents cheating. When we were looking at the responses people turned in and the different connections to planetary boundaries and the different connections they were making to the different things for like looking at green chemistry principles, you could see they were actually all as unique as the students. They weren't just copying off of each other, which is oftentimes, especially in remote learning or when you're dealing with bigger groups where they're just copying. They weren't. They would talk about it, but every single one of their things and their connections they were making were all unique, because they had to pick a unique reaction, they picked a unique literature article, and they did their own analysis on it. And so that was really useful, and that you could actually see their own thought processes, not just either what they think you want them to write down and not just what their classmates wrote down. Also, green chemistry provided a content-rich platform to students to both apply their knowledge and learn concepts relevant to modern organic chemistry, instead of these reactions just being in the textbook. And like it says, like it was even when I took the course, you just kind of memorize it and move on. Is they actually had to see that this isn't just something from a textbook, this is actually something that they needed to learn and understand. And then overall, this project was viewed favorably by most of the students. And so we would like to acknowledge the students who participate in this project. I have been super lucky in that I have really good students every year in our classes. I'd like to thank our undergrad, Jose, who helped analyze the student perceptions on this project. Dr. Delmar Larson and Dr. Joshua Halpern, those two are super awesome. If you guys are thinking about implementing a project like this, go to his office hours. They are super helpful, and they gave quite a bit of feedback and helped like listen to like what I was thinking with the project and gave guidance on how to change it, like modify a little bit, tweak it, and how it can be implemented, which was very, very helpful, especially for someone just learning how to do this. Like they're super awesome resources. And then I'd like to thank all of you for listening. And this research was supported by the NSF EPSCoR grant. And with that, I'd like to ask if there are any questions.
Krystal, there's one in the chat. Oh, two in the chat.
Yes. Yes, there are plenty of reactions to do this again with new problems. The 39 were just the biggest reactions from that textbook. And so like you can pick lesser known reactions, but are still the key ones that students need to learn, or you can have students work in groups. So there's lots of different options for that. And you can also have students start looking at things from OChem 1 as well. Yes, I can. Delbar, I know you, or Jennifer, is there a way I can share my slides, or how does that work?
Yeah, if you want to send them over, Krystal, we'll make sure that we get them disseminated. We're trying to decide the best place to put them, but for now we're going to put them up on the blog post with the schedule so people can easily find them.
Thank you. When can we switch to OChem textbook? I'm not sure what you mean by that one, Delmar. For when can we switch a OChem textbook over to a green text?
Actually, the question, what I was trying to say, I'm sorry, there's construction going on outside. one of the things I'd be excited to do, and I love what you did here, is to be able to take the resources that you've done in order to go back to an organic chemistry textbook that is not green, which is like all of them, and make it into a green organic chemistry textbook. So you can actually implement this into the pedagogy and change things forward instead of just basically being an exercise that really helps the students at the time that you had given it. And that's the true impact of what OER is to be able to build upon it and move forward. And you've done a beautiful job in order to start that process.
Jill?
Is that a clear question? I'm not sure if it.
I didn't catch the question part out of it, or more of a statement. Was there a question part in it?
I guess the question is, given the content of a standard organic chemistry textbook, how many times do we need to do this procedure that you have in order to be able to go back to that textbook and make it a green OChem textbook? I'm just trying to figure out the general scope of making something that's I really think is very powerful, and what we need to actually be pushing more in today's world, and technically in yesterday's world, but we didn't do it in order to implement that. And that requires not just taking the pedagogy that you're doing and implementing it, but the results and then folding it back into the book. And I don't know how much effort it's going to take in order to do that, because I don't know the magnitude of organic chemistry. And that's because I'm a physical chemist, which of course rocks, but nonetheless, I'm trying to put this in context here.
I think if you did this within about 2 to 3 cycles, if you have a small class like I had, you'd have enough of like the good key reactions to actually have it implemented in, because then you'd have key reactions out of every chapter if you did it about 2 to 3 times.
And you published this already yet, or is it still in
It's
review?
been no, it's been accepted in the Journal of College Science Teaching, but they have a really long publication time, so it's gonna be in press for like another year, up to, because it said up to 18 months as of like last summer.
Yeah, all these journals are notoriously slow when you're not in the research traditional publishing research thing. It's painful. It'd be great. Do you have a preprint of that that you're able to share, or a link to that might be available for people to review?
I have the original document, but they don't do preprints on their website.
Okay. Well, if you're willing to share that with your slides,
yeah, I can send you that one.
Then please do so. I think that would be a great opportunity in order to get that out. I do know that I've had conversations with people about doing this in inorganic chemistry, which is even more outside of my forte than organic chemistry. And they're interested in like CO2 solvents in order to be able to do the reactions and such like that. So it'd be interesting to see how this sort of approach can be expanded into other fields of chemistry, at least.
Okay. Alexi just says that we can use ArcSci perhaps for sharing the publication.
Krystal, Robin wanted to know about some of the resources you mentioned, and if you can provide links to the math and drawing resources.
Oh, yep. And I do have it on the bottom of that slide too for the MathPicks one. Right here. But yeah, I can copy that over too. But yeah, it is in slide 5 with the MathPicks snipping tool.
Thanks, Krystal. Yeah, I couldn't see it either.
So. No worries. I just mean is that yeah, I do have all the thingies included on these. So yeah, I will get those out, is what I was trying to say. So yeah, no, MathPicks is super awesome. Delmar, you're the one that told me about that one, and I absolutely love it.
You know, MathPicks has a new feature that will actually render organic chemistry molecules in some special library in their LaTeX interface, which is not standard for LibreText. But I was particularly excited in order to be able to do that. And I think it might be able to take a organic chemistry molecule scan it in, and potentially get the smiles or the cast number or something off of that, which would be radically beautiful. I mean, the people who do that technology, it's unbelievable. I'm rarely so positive about technology, but these guys, they did it right every single time. It's beautiful. So are there any plans in order to do this again this upcoming year? Or was this just too painful for you guys to do and you want to relax?
I have not taught this year. I've been on a RA both semesters, so I did not do it this year. But in future years, yes. When I eventually actually start teaching again.
Great. Are you presenting this in BCCE?
I trying to think which one I'm doing there. I don't think so. That one I'm gonna do 2 other projects.
Okay. We'll have a table there, so feel free to stop by.
Sweet, will do.
Mhm.
I think the GCE, I'm doing this as part of the other one. This one and then our other one's kind of together. I think it's at the GCE. I think one of them.
Great.
Any other questions?
I have a question maybe to Delmar and Krystal. So is MathPicks, is it totally free or is it partially free, or that cool features that Delmar was talking about, are they free?
The MathPicks is a commercial product. It allows, I think, 50 free picks, OCR things per month. And then if you want to go above that, you need to pay for it. And it costs $5 or $6 per month in order to do that. And then you have a near infinite number of individual picks. And the nice thing about that is you can upload a whole PDF and it will convert it over to LaTeX for you. So I found it to be unbelievably time saving in terms of the efforts that what we were doing for both of those things. And like I said, it was like a month ago that I was playing around accidentally when I was scanning, and I just grabbed a molecule and it just popped up, and I'm going, whoa. And I might be able to pull it up right now if you have an actually not on this computer. But it's pretty, but there's documentation there. And if you can't find it, then just let me know and I can pull up and show you it. It's really, really cool.
And you get extra free picks if you share it, or if you have someone else sign up, or you do a referral. So that's kind of what we did too, is we just have people like refer each other. But yeah, otherwise they get lots of free ones each month anyway. Or you just use multiple email accounts and just start referring yourself.
Okay. Thanks.
Any other questions? Well, okay. Thank you, Krystal. That was wonderful.